it's going to help you determine whether a particular function is continuous or it's got breaks in it. Now, it's very, very important that you also know the types of what? The types of continuity that you are having. Okay? Because there are certain questions where they'll say define the continuity, or rather, this is the question: is it continuous? So there's a test which we call the continuous test. So, and we'll look at that. But the key point is that you have to be able to understand and to be able to give and say this is my continuity. So let's start with this example. So if for instance you have that function and then it goes like that. So is this function continuous? Yes, it's continuous, right? It's continuous. So this is continuous. Then when we have that, and then okay, let me use a different color so that let me maintain the red to be for the axis, and then the blue to be for the shape. So you're going to have that, then you're going to have the whole, then you're going to have a function like that. So what kind of discontinuous? So first of all, is this continuous? No, it's not continuous, right? Why isn't it continuous? Because we've got something there, we've got a hole. So we've got a hole there. So this, the type of of discontinuity that we have is what? It's a hole. Okay. Then we are now going to have something else, which is if we have that and that, and then what you are getting is this side you are getting a value there, and then this side you are getting a value there. What you are having, that's a discontinuity, which you call what? A jump. Now, okay, so let's just look at the last one before we can I can then explain how you can determine these things. I'm sure you've done what you call the piecewise functions, right? So the piecewise functions, that's where we understand all these things, right? And those are the questions that you are asked and say, is this continuous? Huh? But it's when you understand these concepts that we are reviewing that you'll be at a better place to what? To and so let's so there's a vertical asymptote, and then we have uh, that, and we have that. So what kind of discontinuity is this? Infinity. Infinity. So so you see here it's what? Positive infinity and negative infinity, right? So you see going upwards, it can continue going upwards, and then there it's going downwards. So so now they are what we call a removable discontinuities. So you may remember that doing our graphings, right? That doing our graphings, they would have doing graphings would have maybe say a function which was like this, and then maybe we so would have maybe something like that, and then would have something like that. I'm just giving an example, and then would then write that and that. So here we use a difference of two squares, right? So using the difference of two squares, what we then have is what? We would cancel that, right? So the moment we cancel that, what then are we looking at? We are looking at so that's a whole. Okay, so we know that that's a whole, right? So one thing about these discontinuities that we've talked about is that the whole is a what? Is a removable. So you can remove a whole. Okay, so a hole is what? A hole is removable, as you've seen from that example. So you can remove a hole. So you can remove a whole. Okay, but for these things, jump, it's non-removable. It's non-removable. So this is very, very important to what, to take note of, because uh, with this, then you can get to appreciate those discontinuities. Huh? So now let's now see just from a couple of examples how we can use this, and then we can go to our piecewise what, piecewise functions. Huh? So what we are going to now do is, for instance, you are asked this, so then you asked and say, uh, is this function continuous? So is this function continuous? And if not, tell us what kind of discontinuities it has. So first of all, what do you look at? If you want, anyway, you can start from the denominator, right? So you see here, if you plug in x, if you plug in 5, you're going to have a what? An undefined. So you say x should not be 5. And what is this going to be? An asymptote. Right now, you know that when we have an asymptote, that's a discontinuity, isn't it? That's an infinite discontinuity, isn't it? But yes, like for this question, okay. So basically, what we are saying is this particular function, this particular function, uh, if you plug in 5, into this function, you know that you're going to have a what? The denominator is going to be 0. And what happens when our denominator is 0? When our denominator is 0, what happens is, it's undefined, right? So what kind of asymptote are you sorry, not asymptote, what kind of discontinuity are you going to have? So it's as though you have that x is what? X is 5. Then depending on the graph, it's going to come whatever ways, but the point of the matter is it's going to have what? Either positive infinity and what? And negative infinity, right? Because this is how things get arranged about an asymptote. Now you may be wondering, it's okay, but why didn't we make even x plus 2 to be an asymptote? Because it's in the denominator, and so meaning that we are not supposed to have negative 2. Now remember, we said what is unique about this x plus 2 is that we can cancel it, right? So we can remove. So in short, remember that when we were graphing, we were having times where I would reduce a function to this, right? From what we had there. So now you see that we've removed that, isn't it? So this particular discontinuity can be removed. And which kind of discontinuity can be removed? It's only a whole, which can be what? Which can be removed. Yeah, so that's basically about this. Has your question been answered? Okay. So another example. So okay. So now another example that we want to look at is this. Is this continuous or discontinuous? And if it's discontinuous, tell us what kind of discontinuity is there. So what do you do in this particular equation? So we know for sure that x shouldn't be what? X shouldn't be 0. So if x shouldn't be 0, then what then we are looking at is yeah, so what then we are looking at is, let's start. So we know that the numerator, is always going to be what? Always going to be positive, right? So it's the really the denominator that's going to really determine. So if x is less than 0, so we know that the denominator always be positive, right? Because of that absolute value, right? But the numerator is the one that can have a negative value. So it's going to be what? It's going to be negative 1, isn't it? Then if x is what? X is greater than 0, we know that the numerator can only be what? Can only be positive because it's an absolute value, right? So it's going to be positive, and then below it's positive because x is greater than 0. So you're going to have what? But so what does this tell you? So it tells you that at where x is 0, we are having two conflicting what? Two conflicting values. So when we plot those values, we are going to get one is here. So meaning we are having so remember greater than, and you know that's not shaded because x should not be 0, right? So that's why that thing is not shaded. Then for negative 1 again, going where? Going to the left. Okay, so you see, so now that's the discontinuity that we have. So what kind of discontinuity is this? So you call this a what? A jump discontinuity. A what? A jump discontinuity. So you see how the jump discontinuity occurs, right? And we'll look at it when we'll look at things like this when we look at the piecewise functions, right? And we'll be able to appreciate. So, but usually the jump discontinuity occurs in cases where you've got a what? Where you've got the absolute, the value or the absolute thing on top there, right? As the numerator. So that's really the thing. So an absolute value function, you are going to have that, or a piecewise function as we'll look at. Okay, so again, is this removable or not? It's non-removable, isn't it? So NR, non-removable. So that's really about it. So let's now look at the piecewise function. So now we've now started looking at continuity. Then from continuity, that's where now we start differentiation. I'm sure you know that that's how your calculus goes. So that's how your calculus goes. So the piecewise functions, at times these can look to be discouraging, but the key thing is just to understand the concept and you'll be good to go. So then, now, why is this part very, very important? So, with regards to what we are, so, so what we are looking at, so this is a piecewise what? So this is a piecewise function, and so for a piecewise function, you always want to look at these functions that you have, right? So by these functions, I mean 5x plus 3, x squared plus 4, and x cubed, right? Now, when you look at all these things, there is no, you're not having anything that's x over maybe something like that. You're not having anything like this, right? So you're just having normal functions without anything really having a denominator, because when we have a denominator, that's where we really get worried. That's why we're really concerned to say, uh are we really having are we having any discontinuity because x is not supposed to be this, and because the denominator would be that. So if you see that these functions which you have, they are okay, like there is no way you can have discontinuity in them, then you now begin to get concerned with these points. These points, I'm going to use a different color and this point. So you've seen that I've shaded the first two in blue and the last two in what's this, in black. So why I've done that, it's because I want you to appreciate something, is that this function, you know that all these functions, all the three have 5x plus 3 x squared plus 4x cubed, there's no way they can be discontinuous, but it's where these functions, so the piecewise function is like this. All these three functions are part of one bigger picture. Okay, so now where discontinuity can usually occur at this point where these particular individual functions are meeting one another. That's where discontinuity where usually happens. Okay, so that's where you are most likely to get a what, to get a discontinuity. Okay, so then it then becomes very very important to be able to say, okay, so let me assess what was the value of this function, or what was the value of this function when x was 1. Okay, because you know that this is the function that this is the equation that this function will have when it's less than what, when it's less than 1. Then this one, it's when it's greater than 1 or equal to 1, but less than 2. Then the last one is when it's the function is greater than 2 in terms of x values, right? So then you're asking yourself to say, if this is continuous between this one, the first one and the second one, then when I plug in 1 in the first equation and I plug in 1 in the second equation, when I get the same answer, then I know that this particular function is what, is continuous. Okay, then you know that this particular function is what, is continuous. So that's something that's very very important to take note of. So what do we do? So we say, so the first equation we plug in 1, so we plug in 1, we have 8, right? Then we go to the second one, we plug in 1, we have 5. Are these the same when x is 1? No, they are not. So you see that there's what? There's discontinuity. Okay, so there's discontinuity there. Then you now assess also this particular point here. So let me use it in black. Let me do this in black. So again, you are saying from this point and this point. So in this equation, so let's remove the blue. So let's now from this equation to this equation, as they are changing from less than 2 to 2, what is happening? What is the value? If it's continuous, their values are going to be the same. Then you know that what, because for this first one, it means that the first one was at 5. Oh, sorry, the first one was at 8. Then the second one was at 5. So meaning there's a discontinuity there because there's a break in the values, isn't it? Okay, so one to assess also for the what, for the second one. So for the second one, we do the same. Plug in what? Plug in 2 in that second equation, right? So you are going to have what? 4 plus 4, that's 8. Then for the third one, so yeah, for the third equation, that's what? That's 8. So you see those values are the same. So therefore, at x is 2, you see that this is what? Continuous. So that's basically about it. So you see, it's very 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 important to take note of this. So if you want, you could tell that, okay, this particular discontinuity that I'm talking about, it should most likely be a what, it is most likely to be a what, to be a jump. Okay, because the function is coming, it's at 8, then all of a sudden it just drops and it's at 5. So you see, right, there is a jump there, isn't it? So that's basically how you deal with the what, with the piecewise functions. So okay, so let's see if we can look at now. So now that's how you do the piecewise functions. But of course, they won't just let it be so like this. Huh? So they'll try to add some spices. Huh? So what they will tell you is, um they may give you a question and tell you say, so they would give you a function like this. So let's look at this function. So now what we did was just the basics. So now we want now to see if we can actually utilize the knowledge that has been gained from this. So you say, okay, so now what then they're asking you is, uh, find the value of c if this is continuous. If this is continuous. If this is continuous. So first of all, what's going to happen if it's continuous? If it's continuous, it simply means that if you plug in a 2 in this function and you plug in a 2 x2 in this function, you're having a sort the same value, isn't it? That's what continuity means. It means that when you plug in the value x is equal to 2 there, you're basically going to get a what? You're going to get a value which is going to be, yeah, so you're going to get a value which is going to be the same. Okay, so let's go. So we know, of course, to say when we plug in 2. Okay, so let's just write first. Let's just write. So we know that if this is going to be continuous, we know that cx plus 3, I'm just writing the equation, 3x plus c is going to be equal when we plug in what? When we plug in 2. Because they've told us that this is what? This is continuous. So there shouldn't be any break in the value. And there shouldn't be any break in the function. And the break in the function can only occur when there is discontinuity, right? So for this one, we substitute. So we have 2c, 3, 3c, and what? Oh, sorry, pardon me. This should be 6, huh? 6, then c, isn't it? So then we are going to say 2c minus c, then 6 minus 3, then we are going to have c minus 3, isn't it? So this means that if this function if c has got a value of 3, what's going to happen is that you are going to have that particular value, right? So that's really the key thing there, right? So c is going to be 3. Okay, so that's how you can go about. So this is just application, huh? So application of what has been already discussed. So maybe we can just look at the last question before we can do the continuity test. And once we've done the continuity test, then we are done with this topic, huh? Or not this topic to say, but this subtopic, huh, of limits and continuity. Then we can now start differentiation from using first principles. Okay, so then, Okay, so they've told you that this function is what? This function is continuous. Okay, so this function is why this function is continuous. So if this function is continuous, then you know that there are no breaks in this particular function. So it means that what you do is that you know the potential points for discontinuity are where between one and this one and the 4 and the 4. So what then you're going to do is that you're going to say, okay, uh let me make an equation using, I know that the value that I'll get, because this function is continuous, so when I plug in 1 into the first equation and I plug in 1 into the second equation, I'm going to get a what? The same value. So let's take it step by step like that, right? So what you're going to have, so you plug in a 1 there, you're going to have a, okay, let me not skip parts. So let me not skip stages. So you have a, why do I keep, okay. So let's do this. So we're going to have ax plus 5, then you have x squared minus bx plus 9, right? So let's plug in 1. So you plug in 1 in this, you're going to have 1. There you plug in 5, then you plug in 1, then you plug in 1, then you plug in, okay, great. So what are we going to have? So we have that. So then what we are going to do then is, so we bring the b, this negative b becomes positive b, isn't it? Then this side has got 1 plus 9 minus 5, right? So this is going to be what? A plus b is equals to what? Is equal to 5. So that's our equation 1. So we're definitely going to do the same thing for the second part as well. So for the second part, again, we do the same. So we are going to say uh, our equation is, so we do that. So we do that. Then, so why are we equating the first, the second, rather the second and the third equation? Because they've told us to say this is a continuous thing, right? So why are we? So we've got that equation 1. So now we are now looking at that. So let's now, for this one, we are now trying to do the same. We know that if this is continuous, then you know that these two things are going to be equal. So what are we substituting in this case? Remember, we are substituting 4. Huh? We're substituting 4 because those were the parameters that we had there, right? So where there is x, plug in 4. So that's a 4 squared, right? Then you have that, then that, right? So you're going to have 16 minus 4b is 9. Then that's 16a minus 4b. Okay, let me write that properly. So that's minus 4b. So that's minus 4b minus 7, right? So let me just extend my page. Okay, so you have that. So then, so what then you're going to have is, so we know that, okay, so let's do this. So you're going to say 9 plus that, so that's what? That's 25 minus 4b. Then we bring, okay, let's try to, okay, let's just simplify it further. Okay, so we've got 16b, and then there is minus 4b, then minus 7. So what we are going to do is, let's take the numbers on one side and all these things. Okay, so we bring 25, and then the 7 is moved, right? So it becomes, from negative 7 it becomes positive 7, right? Then negative, then, so we've done that shift, right? Then we then move also the what? The negative 4 to the right. So we've got, okay, so we've got that. Then this negative 4b that we've gotten from the right is now, so I'm going to write it in red. Huh? This now becomes a what? A positive 4b. So I've just written it in red so that we can keep track of it. So after we've done that, then we'll have something. So those cancel themselves, right? So we're having 30, that's 32, right? So 32 is equals to 16a. So then you're going to have your what? So you're going to have, oh, there 16, there 16. So your a is equal to what? Your a is equal to 2. So now, so that's there. So we've got, now we now look at our equation 1. What was our equation 1? So our equation 1 was a plus b is equals to 5. And then now we've got a, which is equal to what? A is equal to 2. So you have that. So there you have it, right? So what we've just done is basically using what we've learned and then being able to apply them in these things, right? So that's something that's very, very important to take note of. Okay, so that's pretty much about it. So now let's now go through, since we've now done pretty much everything on it, on continuity and limits. I just want us to go through the 3-step continuity test. I think once we've done that, I think that should really be able to do it for us. Huh? So I think that should be enough for us to do on this topic. So what we basically do for this one is this 3-step continuity test. So 3-step continuity test. So 3-step what? Continuity test. So what happens for the 3-step continuity test? These are things that you can use anytime you've been told to, to say whether this particular function is continuous or not, making use of what? Of limits, okay? So what you first want to do is this. The first condition. So the first condition is that, so the question would be, is this function defined at, let's say, when x is equals to, maybe let's say a, so that's a. So what you first want to find out is f of a defined first of all? Okay, so is f of a defined? So that's the question that you want to ask us, or rather, what this particular equation or function you are looking at should be one where f of a is what? F of a is defined. So we know what is f of a. F of a is just basically saying when you get a number, you plugging into the function, you are getting a value of x. Because if you plug in something in a particular function and you can't get an answer, then there is no way that that, then you even end, because there's pretty much nothing that you can do there, right? But of course, that's where we're doing all those manipulations, where you try to factorize, you try to do this just to try to ensure, just to try to ensure that maybe you can be able to break it down in one way or the other, right? So that's the first point. So the function has to be defined at that particular value. Then what you else you want to do is that the limit a so the limit as x goes to a for that particular function must exist. Must exist. So why should it exist? Because remember, what do limits tell us? If you've got, let's say we are focusing on this point, right? If we are focusing on this point, and this point, let's say it's x a, and then we know that f of a is maybe, let's say, 5, isn't it? So what's going to happen when we get a limit, when we are coming from the left? Okay, so remember the way we do a limit when we are coming from the left. So when you're coming from the left, you say limit of a of x as goes, you then put like a minus sign, right? Of this particular function is what you're going to say, oh, okay, when I do this, my value is what? My value is 5, just using this example that I've drawn here. Then when you're coming from the right again, like, oh, coming from the right, okay, you do that. So you put like a plus there, right? Show that you're coming from the right. So your value is what? Is 5. Okay, so your value is 5. So what does this tell you? It tells you that, okay, when I'm coming either from the left or from the right, both are giving me the same what? Are giving me the same limit. Therefore, it tells me that, yeah, I'm going to meet at what? At this part. So this particular function, as x is going towards a, the values are coming closer and closer to what? To 5. And so it means that this limit what exists. So that's how you test whether a limit exists. Okay, so that's how you test whether a limit exists. So when you're coming from the left, coming from the right, the value has to be the same. So I just wanted to make that sketch because it would be I thought to be easier rather than just explaining it, right? So what's the condition for this? The condition, I've already explained it, so let me just write it down. So that's the condition. So that's about it, right? So yeah, so the function, so the limits have to be what? Have to be equal. Then the other thing that then you'd want to do, the other thing that you'd want to do, or rather the other thing that you want to check for is the third thing, and it's equally important, I would say. So the third step of the three-step continuity test, you are saying the limit. So you are saying the limit of f of a of sorry, the limit as x goes to a for f of x is equal to what? Is to equal to f of a. So like for that equation that we looked at, oh sorry, so like for this example that I gave us, right, where we are saying when you are coming, okay, so here is our point, and then like that, right? So this is our x is equals to a, and the value when you plug it in, it's 5, right? Okay, so now if you are coming from this point and this point, like we said, you're having your limits being the same to be 5, isn't it? So your limit is 5, like we found. Okay, then also your f of a is 5. So yeah, that's what basically is. It's saying that your limit when x is approaching a is equal to what? When is equal to the f of a. So it basically means this just proves to say, and it makes logical sense because you're saying, if you are saying as you are approaching a, your value is approaching 5, and then when you plug in a into the equation, you are getting 5. That then makes sense to say no, then your limits are actually correct, and then it means that this is very continuous. But you can imagine if your limits are saying maybe 5, and then the f of a is saying maybe something like 10. That means that then there's a discontinuity there, because how can your limits, which are pointing you to this point, have a different value from the value of the function at that particular point? So these are the three steps that you have to take for a continuity test. Okay, so that's the key thing with regards to these things. Okay, so let's look at an example. So look at a piecewise function. Okay, so here we've got a piecewise function, and then we've been asked to say determine if this is continuous at those points. Okay, so of course our points of interest, like I said earlier on, will be at 2 and 3, right? So what thing do we want to first find out? Remember, the first point said what? You want to determine if f of that particular value of x exists. Now, between the first and the second equation, which one are we going to use to find f of 2 for this function? Now, this is very, very important. So remember, look at this symbol, right? What does this symbol say? That symbol says x is what? Uh, x is less than 2, isn't it? So that's what that value says. So it means that if you are looking for x, do you use that function? Or rather, if you are looking for f of the function 2, if you are looking for the value of x at 2, do you use that function? No, you don't, because this particular function, the first one, only works when x is less than 2. Let's now check the second one. The second one then says x is less than or equal to. So that's why you have to be very, very careful for these things, right? So you see that for this one, so we'll use the second one. Why? Because in its domain, okay, we've got x being 2. Okay, so it's less or equal to 2, less than 3, isn't it? So I mean that when we're trying to find the f of 2, we are going to use the second equation. Okay, so we do that. Okay, then now, so we've done that. Now let's check now for the second thing. What do we say for the second thing? We check the limits when we are coming from the left and when we are coming from the right, isn't it? So we are doing that. So limit, so you are checking the limits. So we are checking the limits as you are coming from the what? So you are checking the limits. So you are checking the limits as you are coming from the what? From the left. So you do that as you are coming from the left. You have that, and then you're going to have okay. So now, which one are you going to use? Which of are you going to use, the first one or the second one? So remember, you are coming from the left, right? So if you are coming from the left, that's less than 2. Okay, so that's less than 2. So because that's less than 2, what that entails is that So what that particular thing entails is that you are coming from what? From less than 2. So what's going to happen to this particular thing is you're going to use the first what? The first equation, because it's the one that talks about what? About less than 2. Okay, so you're coming from the left, isn't it? So you're coming from where 2 is less, or rather from where x is less than 2, and then trying to approach what? Trying to approach 2, isn't it? So we use the first equation. So that's the key. So here it's just about taking note of these things, because so you plug into, so it's about taking note of these things, because it's these same things which make a very huge difference as to whether someone gets the question right or wrong. So then we know that we are going to have square root of 4, and square root of 4 is going to be 2, right? So now let's now come again, limit as x approaches 2, but from the right side, right? So that's a plus there. So we know we are coming from where? So now here we're going to use the what? We're going to use the second equation, isn't it? Second equation of the piecewise. So we're going to use this and that. So we're going to put 2 there. So we put a 2 there, we put a 2 there. So what you're going to have is 4 minus 2, which is going to be 2. Okay. So now you're asking yourself, these are equal things, okay? For coming from the left and from the right, they are equal. So what does it tell you? It means that there's the limit. So it means that for this particular function, when x goes to 2 from either side, so that's why I've not indicated, it's because from either side is 2. So now, so this is very interesting. So why are we saying that the limit is there? So the limit is there because coming from the left and coming from the right gives us the what? Gives us the same thing. So now we can now make the third statement. So the third statement, remember what we are saying is that the limit as x approaches 2 for this function, and f of 2 is the same value, which is 2, isn't it? Okay, I know that we are running out of time, but let's just finish this so that we don't. Yeah, we are just doing the same thing, but just for 3. Okay, so we'll just be relatively quicker. So that's basically how you answer these questions, right? So you find the value of the function at that point, you find the limits coming from the left, coming from the right, then you check whether these are the same. If they are the same, then the limit is there. Then you check if the limit and the f of x for that at that particular point, if they are the same. If they are the same, then you say what? So this is continuous. So this particular function is continuous. So it's continuous at x is equal to 2, right? So that's something that's very, very important to take note of. So let's now go now to the second part of our question. So the second part of our question, so again, like we said, which equation are we going to use to find the value of this function f of 3? We use this particular part which has got x being greater or equal to 3. Why? Because it's got the part for what? It's got the part for greater or equal to. So you always go for the function which has got equal to for that particular value which you want to plug in. So here we're going to use the what? The third equation. The third equation. So you plug in 3. So that's going to be 6 plus 5, so that's 11. So then now we go again for the second part. We are trying to find the limit. So we're trying to find the limit as x approaches 3 from the left. Okay, so approaches 3 from the left. Which function are you going to use when x is less than 3? Remember, from our piecewise function, you use the second equation, right? Of course, the reasons being the same. one that are the same reasons that I gave for the earlier part. So you're going to have that's going to be 9 minus 2, so that's 7, isn't it? So you've gotten the 7 there. Then the limit when x is approaching 3 from the right. So what you're going to have, so which function do you use? So for this one, you're going to use the third one because that's where you are coming from the right, right? Greater than 3, yeah? Because, yeah, for the same reasons that I gave on the uh, earlier example. So you use that, so you plug in 3 on the third piecewise equation. Then what are you going to have? You're going to have 11. So you see now that the limits when you are coming from the left, when you are coming from the left and when you are coming from the right, they are not the same. So therefore, the limit when x approaches 3 does not what? Does not exist. Does not exist. Okay? So of course, once you figure out that it doesn't exist really, we are almost relatively done. So if they are not, it means that there's some discontinuity somewhere. That's why they are not in agreement because there's some discontinuity. So now our third step is going to be, yeah. So you know that of course your, since you remember the third step says what? You compare the limit with the f of 3. Now you don't have a limit, so there's nothing that you can compare. So you just say there is discontinuity. There's discontinuity at what? At x is equals to 3, isn't it? There's discontinuity. Now, what type of discontinuity do you have? So, first of all, is this a discontinuity that you could remove? No. So this is not a whole, isn't it? Is it a discontinuity that involves a vertical asymptote? No, this doesn't involve a vertical asymptote. Therefore, is this a discontinuity where you're having two different values? So you're having here, let's say our y-axis is here. So you're having, when you're coming from the left, you've got 7, then coming from the right. So it's almost like this, right? So you can picture it like here there is 11 and here there is 7, and then this is your x or y plane. So that's basically what our function is representing. So what kind of discontinuity we said that was? So you say this was a jump discontinuity. So basically that's how you use the three-step continuity test. Okay, so that's how you use the three-step continuity test. So when we meet on Wednesday to make up for that, so we'll be able to start now with differentiation.